Okay, last assignment for this week. And on the first assignment, I said that we would show you how to write equations yourself. We told you the equations. Today we're going to show you how to write the equations. It's not that difficult, actually. All growth equations start off like that. All decay equations start off like that. R stands for the rate. T stands for time, etc., etc. A stands for initial amount. So, here's your assignment and notes. We're going to do this whole first problem together. The second problem, together, and then the third, fourth, and fifth problems you're going to do by yourself. Yeah. So, either that is genius on my part or lazy on my part. You decide. Number one. Oh yeah, I forgot today's date. What's today's date? June 4th. Almost done. Yeah, 420. Look at it. I'm just gonna leave it like that because it's funny. Oh, shoot. Now I can't think. Anyways, there are currently 8 bacteria in a petri dish. That's not possible, by the way. It could be 8 million, 8 clusters, but whatever. 8 bacteria in a petri dish. The number of bacteria increases. So you got to pay attention to the words. This particular word tells you it's going to be a growth problem. Yeah. So we need a plus sign. Voila. So here's how the equation starts off. Y equals, the initial amount always goes first, that's the A value, and then times 1 plus the rate, 25% to the power of X, and then you go like this. Obviously percents are not real numbers, you have to change that to a real number. 25% means 25 out of 100. 25 out of 100, which is 0.25. So, on the previous day's assignment, the equations that we were giving you looked like this. And that's where they came from. So we tell you the growth rate. By the way, the way that you can tell something is linear versus exponential is very subtle. You have to pay attention to the words, but we have 25% every hour. So these words, way back in first year algebra when you studied rates, you learned that the words per, each, every, all mean the same thing. So I could say $25 per week, $25 each week, $25 every week, and it means the same thing, right? So in this situation, the way that you know it is exponential is you have 25% every hour. So when you get two of these words together, it's exponential. If we just said 25 every hour, that would make it linear. But the fact that there's two of these words together makes it exponential. So, very subtle difference. Yeah. Now we have to fill out this table. You do not have a graphing calculator. Oh, hey, maybe on how about this? I will send you guys a link that allows you to download a graphing calculator onto your Android phone. I don't know how to do it for iPhones, but I'm sure there's a way, so just look it up on the internet. Graphing calculator on iPhone. Find a free app, download that app to your phone, and it will make the table for you. But I don't have a graphing calculator, and I'm assuming you don't, so we're going to have to do this tediously. 0, always gotta have 0. 5, negative 1, negative 2, and here we go. The equation, 8 times 1.25 to the power of negative 2. H stands for number of hours. B stands for number of bacteria. So, and negative, what does negative mean? That means 2 hours ago there were about 5 bacteria. Yeah, we're not. 5 is good enough. You go round to the nearest whole number if you want. And how about 1 hour ago, how many bacteria were there? 6.4. Okay, I'm gonna the math teacher in me cannot do it. I was gonna leave it whole numbers, but I can't. I just can't. 8 times 1.25 to the power of 0. Of course, the answer is 8. 0 always stands for y-intercept or starting amount. And then 8 times 1.25 to the power of 1. 10. So after 1 hour, there are 10 bacteria. 1 hour, 10 bacteria. You cannot tell that it's exponential growth yet. Like if we didn't give you the equation or a graph to look at, and we only told you those two numbers, 8 and 10, you can't tell it's exponential. It could be exponential, linear, quadratic, polynomial, it could be anything. You just don't know. You need more data, which is one of the things I was trying to tell you about math in the previous video. Is the more math you know, the better you understand how the world works. Okay, 8 times 1.25 to the power of 3. Oh shoot. 25 to the power of 3. Bam. So after 3 hours, there are 15.625. Like I said, it's not possible to have 15.625 bacteria. Not possible. But if you studied biology at all, you know that there's no such thing as, okay, there is such thing as egg bacteria, but that's not detectable on a test, right? A test could detect 8 million bacteria. So we could call this 15.625 million bacteria. Yeah. To the power of 4. Actually, there might be some tests. There are very precise tests. I'm not going to write all those numbers. That may be able to detect minute amounts of bacteria or steroids in your system. How do I know this? You don't want to know why I know this. To the power of 5. 24.4. So, after 5 hours, remember H stands for hours, B stands for bacteria, there are 24.4 million bacteria, whatever. Sketch. You're not actually graphing. If we wanted you to graph, we would put grid lines on here. We want you to sketch. And just like on the previous assignment, we want you to know that exponential functions are curved like that. This is a growth problem, and we also want you to always tell us how many bacteria there were initially. That is the y-intercept. 8, 8, 8. Yeah. And then these two questions right here tell us if you actually understand how to apply math to the situation. And the reality is, if this is all you could do, you don't really understand math. The purpose of math is to apply it to real-world situations. Yeah. So, I love story problems. That's the only type of math problems I like, is story problems, because it's all this other stuff, that's boring. This is no fun to me. But answering these questions, that's fun. Okay, so approximately, how many bacteria would there be after 24 hours? How many were there 2 hours ago? So, unfortunately, we're asking you two questions. You're going to do whatever. Sorry, guys. So you write the equation. 8 bacteria. Growth rate 1.25 to the power of 24. And then plug that in your calculator, and that'll tell us how many bacteria there will be after 24 hours. 1 day. It's going to be a lot. That's the power of exponential growth. So after 5 hours, 24. But watch this. It's about to be a crazy big number. 1,694. 1,694 bacteria. I don't need a complete sentence, but I do need a label. So the question says, how many bacteria would there be after 24 hours? About 1,694 bacteria. So I don't need a complete sentence, I just need a label. How many were there 2 hours ago? Well, we have it in the table, but let's pretend we didn't have it in the table. The fact that we are telling you to go backwards in time implies that the exponent is going to be negative. And you thought there was no purpose for negative exponents. Well, think again, suckers. That is the purpose of negative exponents in real life. Bam! That means 2 hours ago. That's why we studied negative exponents way back in February. About 5. How do I know that? Because I see it right there in the table. About 5 bacteria. Voila. Yeah. Question number 2. If there are 400 bacteria, I don't know why my dog is barking, how many hours would have passed? Estimate to the nearest hundreds. This is, I hope you have a calculator. That's all I gotta say. So, this time, the number of bacteria is given to us. Remember, this is like X, this is like Y. So this time they're telling us the Y value is 400. So 400 equals 8 times 1.25 to the power of X. We don't know the X. So I'm just going to start guessing. And it says to the nearest hundredths place. I'm going to change that. And I want you to change it on all the problems to tenths. You can do it. You can do hundreds if you want to, but tenths is going to be good enough, okay? So, unfortunately, we are running out of time in class, right? So we can't teach you actually how to solve this type of equations, or equation. Obviously, you divide both sides by 8, but then what do you do after that? I wish we had time to teach you guys. So, we're just going to estimate. I'm just going to start plugging in random numbers. Let's see, after 10 hours. 74 bacteria. Nope. So it has to be more than 10 hours. 8. Let's try 20 hours. Oh, close. So I have to go less than 20 hours. Between 10 and, let's go 17 hours. Bing! Ooh, more than 17 hours. Actually, since you are, it's okay. We'll keep on going. Let's try 18. 444. That's slightly closer. So now I'm going to go 17.6. 8 times 1.25 to the power of 17.6. Ooh, snap. That's pretty close. Let me try 17.5. Bam. And that is closer. So I'm going to write 17.5. X is about 17.5. You need a label. The question is how many hours? So it's 17.5 hours. So after about 17.5 hours, there will be 400 bacteria. That's, I don't know if you guys know this, but inside your body, that's how bacteria grows. It doubles. Every so often, and it grows exponentially. That's why within a matter of hours, you can go from feeling perfectly fine to really crappy when you get the flu. Sorry. Again, I don't need to see any work, just the original equation, and then the answer to the equation. Change place is good enough. Yeah. Problem number 2. This one is a decay problem. Obviously, there's only 2 types. The first one was growth, so this one must be decay. Let's find a word that means decay. You have 1,000 grams of some radioactive form of iodine. That amount decreases. Well, that was easy. Sometimes it's very obvious which word is telling you it's a minus sign. So, again, growth problems have a plus sign, and decay problems will have a minus sign right there. So if you were confused on the first assignment when it said the decay rate of 0.4, but inside here it said 0.6, now you'll understand why. We just didn't want to kill you on the first assignment, you know what I'm saying? Okay. So, radioactive elements, uranium, iodine, etc., they all have a half-life. And I actually don't know if this is accurate, like if the half-life of iodine is a month. But, oh, have you guys ever heard of carbon dating? This is how we know how old, or we can estimate how old dinosaur bones are. We measure the amount of carbon in it. And the amount of carbon in it, we can go backwards using math to figure out how old the dinosaur is. See that? Math in real life. That's exactly how they do it. It's very simple. Measure the amount of carbon, set up an equation, and that'll tell you how old the dinosaur is. Pretty interesting. Okay, so we start off with 1,000 times 1. This is a decay problem, so you need a minus sign right there. And 50% to the power of x. These are exponential problems, so you always need to the power of x. And then you change 50% into a decimal. I know you know already, but I just want to show you again. 50% means 50 out of 100. Percent means out of 100. So divide by 100. 0.5. Okay, and then 1 minus 0.5 is obviously 0.5. Or we could put a half there. That's why it's called half-life. Yeah. And now we complete the table. -2, -1, 0, 1, 2, 3, 4, 5. I probably should read the problem again. What is M? Oh, M stands for number of months. This is your X. I stands for the amount of iodine. That is your Y value. Clear. So we start off with 1,000. And 0.5. So 2 hours ago. 2 hours. Oops. Oh my goodness. What is going on with my, what am I doing with my life? Oh, dang. When you guys do that in class, it kills me, but it happens. Anyway, 2 hours ago, there were 4,000. Oh, how did I know that? When something doubles or cuts in half, it's kind of easy, but that's how I knew it was going to be 4,000. And 1 hour ago, should be 2,000, yeah? 1 hour ago, 2,000 bacteria. Matter of fact, watch this. I don't need no stinking calculator. We know we start off 1,000. It is doubling this way, cutting in half this way as you go down, so 500. 250, 125. Oh shoot, what's half of 125? 60. Okay. Don't tell anybody I'm a math teacher. 62.5. My excuse is I'm hungry and I got to go to the bathroom. That's my excuse. My brain don't work. And then half of 62.5, that's 31.2. I can do that one. Shoot. Now, just in case you think my math is faulty, let's go ahead and do this on the calculator. Pting, 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 to the power of 0. It's going to say 1,000. Okay? Because anything to the power of 0 is 1, right? To the power of 1. Now it's going to say 500. 250. Oh, look at that. Speaking of 50, here's a good math joke. 50 Cent. Everybody know who that is? The rapper, right? What did 50 do when he got hungry? 58. Think about it. I'm gonna say it. Okay. What did 50 do when he got hungry? 58. Why is that so funny? When I first saw that on Facebook, I was dying. Because it took me a second to realize 58. Oh, 58. Okay. Sketch. This is a decay problem, so we need to see. Voila. If you get it wrong, by the way, you need to just slap yourself. You know why? Because we put the picture right there. So you literally just copy this picture here, this picture there. Shoot. Seriously, if you get this problem wrong, slap yourself. Okay. And the y-intercept is 1,000. Start off with 1,000. Voila. Okay. And follow-up questions. How many grams of iodine would there be after 8.5 months? Obviously, we're going to need a calculator to do that. 1,000. Oh. Always use this. You could use either of the equations, right? But the bottom one is the one we want you to use. 1,000. 50% decay rate after 8.5 months. There will be about 2.8 grams of that iodine left. How many grams were there after 5 years ago? So when you see the past tense, that's how you know it's going to be a negative exponent. Negative 5. I don't think I need a calculator. It ain't going to be approximate. Watch this. It's going to be like -3 should be 8, -4 should be 16, it should be 32. It should be exactly 32,000. But let me double check just to make sure my math is right. 32,000. So, again, this is how they measure. You've heard of carbon dating. There's different, I think it's isotope is the correct word in chemistry. There are different types of carbon. The one that they use for carbon dating is carbon 14. This is exactly how they know how old something is, or they're pretty sure. They measure the amount of carbon in it. They set up a simple equation based on whatever the half-life is. Yeah. Actually, it's more like this situation. It's definitely more like this than this. This is what archaeologists and scientists do. Not that. This. So they find something. They go, oh, it has 10 grams of whatever in it, and then they solve the equation. Voila. So we know the y value this time. We don't know the x value, and we are going to use calculator estimate. So when is there going to be 10 grams? I'm going to go 6. I'm going to try 6 first. So 1,000.5 to the power 6. How about after 6 months? Nope. Let's try 7 months. After 7 months. So somewhere between 6 and 7. I'm going to try 6.6. Let me try 6.6 months. Remember, I'm just trying to get close to 10. Hey! 6.6 months. Make sure you label your answer. The label shows us that you comprehend the situation. Anyways, if there are 10 grams of iodine left, how many months have passed? 6.6 months have passed. estimate to the nearest tenths. Yeah. Alright, that's it. So there are 3 problems on this particular assignment. Actually, how about you just do 2? Do 2 of the 3. One of the growth problems and one decay problem. Yeah? So, 2 out of the 3.